Hi, welcome to Module 5, and this is Part 1, starting with Chapter 6 of our text. We're going to begin talking about cloud forms, and the first thing that I'm going to go through is the 4 major ways that I can make a cloud or create airlift so that cloud formation can occur. And the first one is known as orographic lifting. Orographic lifting is when I have something that's actually in the way that creates a deflection for the air. For example, a mountain range. A mountain range is the best example of orographic lifting because the air cannot go through it, so it must go up and over the mountain, creating an altitude change of the air mass. Now, in the previous module, we had talked a little bit about an orographic lifting example as we were going about the adiabatic process, and we talked a little bit briefly about the rain shadow deserts. Next one is frontal lifting. This is when fronts meet, whether it be a warm front or a cold front or a occluded front, one that's a mixed front. When those things collide, it creates a sense of lifting with the warmer air mass going up and over in the various places that it would collide. Next one is convergence. This is when I have a region where I have a hotter surface material, and that creates a natural convergence where the air is converging and rising over that location. We can think of this as a source of low pressure, right? So this is a low pressure source because there's space for air, so all air is moving into that location and going up. And finally, another example of convergence is localized convergence, and this has to do with differential heating in various surfaces. And one example of differential heating would be urban heat island index, which is something that we'll cover later in this course. But basically, as we all know, different materials have different capacities for absorption and reflectivity. We talked about albedo already and how things that are something like a snow-covered mountain has a higher reflectivity or a higher albedo, where something like a street that is made out of a cement has a lower albedo, has a higher process of absorption, lower reflectivity. And so that means that the areas that I have this blacktop surface would end up being a location that would be warmer than the surrounding green grass regions, creating a natural localized convection location. The next process that we're going to talk about has to do with this adiabatic process. We have some different ways of looking at the atmosphere, and all of them can be divided up into various forms of whether the atmosphere is stable, so I can expect no changes in my atmosphere, or my atmosphere is unstable, so I can expect changes in my atmosphere in that location. And right here, there's a little bit of information and title wording. I'm going to go through a quick definition, but please take your time and read. So each one of these slides are well written, and it's something that you can read about, but I'll kind of go through, just like I did with the clouds, a quick overview of what we're talking about. So static stability is the concept that air has a tendency to rise or lift. And while that air is lifting, most of the time it does it on a very specific rate. This is called the environmental lapse rate. In our region, that has a specific number. Our natural environmental lapse rate is 6.4 degrees Celsius every 1,000 meters of altitude. So if I go up 1,000 meters in altitude, I can expect it to be 6.4 degrees cooler than the original surface location that I started with. And I can continue to do that. So as I go up, if I go up to 2,000 meters, I can expect it to be 12.8 degrees cooler at that point of altitude, and so on and so forth. This natural cooling off process is the environmental lapse rate. Now, if I take certain spots where I'm seeing natural rise or natural rates of rise within my air as it's lifting, and some of it happens to be slightly warmer than the air around it, it's going to rise fast, and that would be an unstable air mass. That means that it is rising and cooling off differently. It is adiabatic in its process. When this occurs, I would consider the atmosphere unstable. And so here we go. Absolute instability. So regardless of whether the air is saturated or unsaturated, if the atmosphere is absolutely unstable, that means an adiabatic or lifting air parcel that is moving on its own. And if I consider a little area of air that is moving upwards, so I'm moving on the vertical on its own, I consider it a parcel. That's a good term to use to describe that little air bubble that's moving on its own, not with the surrounding air. It's rising at its own rate in its own spot. If that air parcel is warmer than the environmental air around it, the lapse rate air, the stagnant air around it, then I consider the atmosphere absolutely unstable. And this matters or does not matter whether it's saturated or unsaturated. So if you look in both examples, I have an air parcel here and it's rising up, and at 100 meters, it's dropping in temperature by 1 degree in my air parcel. But if I look at the air surrounding it at the change of 100 meters, I'm dropping down to 8.5. And this is colder than this. So this air is going to continue to rise. Same thing down here, same sort of process. Here I have a saturated air mass, which means my adiabatic lapse rate is now a wet adiabatic lapse rate. So it's going to drop a little slower, which means it's going to drop at half a degree in this case. And so I'm going to go up by 0.5, and I can see that right here because I'm at 9.5. And over here, I can see that this temperature is still a little bit cooler than. Oop, and I flicked. My slide flicked. Sorry. And then it's a little bit cooler than. See? On its little set. So it is 8.5. Now notice over here you see the abbreviations ELR. This will help you read these charts because you're going to be expected to do this for some of the coursework in the labs. And ELR stands for environmental lapse rate. Environmental lapse rate is the stagnant air around it, and it's telling you that the cool off, or the rate of cooling off, is 1.5 degrees Celsius every 100 meters. Where my adiabatic lapse rate, my dry adiabatic lapse rate, is 1 degree every 100 meters, and my wet adiabatic lapse rate down here is half a degree, or 0.5 degrees Celsius every 100 meters. So this example is absolute unstable. Now looking at absolute stable, this is actually one where I'm going to see little to no rise even if there's something occurring. So this is like a forced air. This is air I'm forcing up and over, but I would not expect much in formation of clouds or conditional changes. This is absolute stable air. This is air that doesn't want to rise or change its place in the atmosphere. And we can see this occurring because the environmental lapse rate air is actually warmer than the air parcel itself. So we would consider these little pockets of cold in this case, right? Cooler than. And you can actually see that to be true in my example. And it has nothing to do with the adiabatic lapse rate, because if you notice, my adiabatic lapse rate is the same in my absolute unstable. So here it's still dropping 1 degree every 100 meters. Here it's still dropping 0.5 degree every 100 meters. But my environmental lapse rate air, which is variable, my rate of lapse is variable, is not cooling off as quickly. And therefore, my change in temperature is not very great. Most of the atmosphere is about the same temperature in that example. And so my air is stable. I'm not forming a lot of clouds. I'm not forming or creating a lot of rise. Nothing's rising up quickly. I'm not seeing fast formation of things. I'm not seeing water condense on itself, making a storm-like event. So that's my absolute stable air. My next one is conditional stability. This is where, as I go up in the atmosphere, my environmental lapse rate will change, and therefore part of the atmosphere will be stable and part of the atmosphere will be unstable. So it's like a half and half. And depending on where it's stable versus where it's unstable is comparison of whether the air parcel itself is warmer than the environmental lapse rate air, or if it's cooler than the environmental lapse rate air. And they drew little examples here with the lines. So here we go. This is the dry adiabatic lapse rate again. This is still 10, 9, 8, 7, as we can see, and actually they've zoomed out. But right here, I can see that I'm colder than in this little bubble, so I'm unstable, and then I go back to being stable. So I'm stable, unstable, stable again in my lapse rate air. So conditionally unstable means that some of the time I am in a situation where the environment